Hello, this is Mr. Henry, and this is lesson 4.5, Proportional Relationships. The central question says, how do I use proportional relationships to find the solution to real-world problems? The warm-up question says, what do you think it means if a relationship is constant? So a constant relationship, well, the word constant itself means it's something that doesn't change. If something remains constant, it doesn't change. So a constant relationship would be a relationship that doesn't change. Now, this could be a relationship between two friends. If they have a constant relationship, they're maybe always friends, or maybe they always hate each other, and that's what's constant. Or it can be a relationship between two variables, mathematically speaking. A constant rate, our one vocabulary word for the day, constant rate is a situation where a variable is moving uniformly with respect to time. That means it's moving constantly. It never moves faster or slower. Its speed remains constant. That's what a constant rate is. So if something continues at a constant speed, it doesn't go faster, it doesn't go slower, it always stays the same. So our first example here says, Sam can walk 2 miles in 25 minutes. How far could he go in 94 minutes? Well, we have a little table here. We could start filling some information. I mean, we know in 25 minutes he can go 2 miles. And so if we go, 4 miles, if we double the distance, it'd be double the time. You'd go for 50 minutes. Let's just keep going. So add another 2 miles, add another 25 minutes, another 2 miles, another 25 minutes. And this will at least get us close to the answer. I mean, the 94 minutes we're looking for in the problem would be somewhere in here, between 75 and 100. So, you might guess it's like 7 point something miles. So since this relationship is proportional, because Sam's walking at a constant speed, if this relationship is proportional, we can use a proportion. X variable, Y variable. And so we could say, well, 25 minutes, he can go 2 miles. So time, distance. How far could he go in 94 minutes? So 94 minutes would be a time, and this would be our unknown distance. .25 corresponds to 2. 94 minutes would correspond to some distance we don't know. So we cross multiply. This gives me 25y, and 2 times 94, some big number, 2 times 94 equals 188. Divide both sides by 25, cancels, y equals, it's going to be some number that doesn't work out evenly. Divide by 25. 7.52 miles. Since we're talking about a distance here, distance is the y variable. So in this amount of time, Sam could walk 7.52 miles. The second part of the question says, how many miles y can Sam walk in X minutes? So this is looking for more of a general equation that we could use, a relationship between the X and the Y variables, the time and the distance. And all we really need to do is, we could do the same thing we did here, except if I say, we know X, Y, he can walk 25 miles, or sorry, 25 minutes, 2 miles, x, y. Some random other amount of time and its corresponding distance. If I cross multiply here, I get 25y equals 2x. And because the question asks for how many miles, we want to solve for y. Divide by 25, divide by 25, and y equals 2 over 25x. Basically what this does for us is if we were given any amount of time that he walked, if he walked for 10 minutes, I could throw a 10 in there, times it by 2/25, boom, I get my answer. If they said he walked for 4 hours, well, 4 hours times by 60 minutes an hour is 240 minutes. Again, just plug it in, multiply, you got yourself an answer. So this is kind of like a general form that works for this particular problem. This Sam can walk 2 miles in 25 minutes. This tells us how many miles y he can walk in x minutes. And if you don't like this fraction, you could also use the decimal. Y equals 0.08x. Same thing. And I would like to impress upon you the fact that it doesn't say in the problem, but Sam's walking speed is constant. I guess the problem's not worded properly. It should say, if Sam walks at a constant speed, how far could he go in 94 minutes? But it is important that the walking speed is constant. Because if like Sam walks for a little bit and then he stops for 25 minutes and then he walks a bit more and then he starts running, well, then this would not necessarily be true. This says every time he's walking for 25 minutes, he goes 2 miles. He walks for another 25 minutes, another 2 miles. It's very important that his speed is constant, or else we couldn't do the problem. Letter B. It says, a diver can kick his legs 4 times for each 20 feet underwater he goes. How many times would he have to kick his legs to go 148 feet down? All right, so we've got the kicks and the distance, so they are x and y, just kind of like before. So every 4 kicks, he goes 20 feet. So if we repeat this, we've got 8 kicks would go another 20, and 12 kicks would go another 20. Ooh, that's not 20, that's 40. And another 4 kicks would go another 20, and another 4 kicks would go another 20. So this table helps us just visualize the relationships between the number of times he kicks his feet and how far down underwater he goes. And we want to know how many times you have to kick his legs to go 148. We don't know that. So this is kind of the relationship that we're trying to figure out when we use our proportions. Since these two measurements are constants, they have a constant relationship, they're proportional. So we know if he can go 4 kicks and he goes 20 feet, how many kicks, CK, there we go, to go X feet. So let's see, we want to know how many kicks to go 148 feet. See, kicks, kicks, feet, feet. Cross multiply, we go here. 4 times 148. 592. 20 times by x is 20x. Solve the equations. We divide by 20 on each side. Those cancel. X equals 592 divided by 20 is 29.6. So if this guy kicked his legs 29.6 times, he would go the 148 feet down. And this would be kicks. Now down here, it's asking for that general statement again. In how many feet Y can the diver go in X kicks? So the relationship still stands. Every time he kicks his legs 4 times, he goes 20 feet. So if he kicks his legs X times, he would go Y feet. And we cross multiply, we get 4y equals 20x. Since it's asking for how many y's, we solve for y. Divide by 4, x equals 5. Oopsie, not x. Y equals 5x. That means every time he kicks his legs, he does 1 kick, he goes 5 feet. If he did 5 kicks, he'd go 25 feet. If he did 15 kicks, plug in the number in for x. 15 times by 5, 75 feet. So there's a relationship between how many times he kicks and how far he goes. And it's a constant relationship. Okay? So that's kind of what this is showing. This is showing the relationship between the number of kicks and the number of feet. This is showing the relationship between the distance, or say the amount of time, and how far he's gone. The amount of time and how far he's gone. A little in-between summary question says, why does it matter if the relationship between the variables is constant? We'll answer that question. Why does it matter? The answer is because if it's not constant, then the relationship's not proportional. It's not linear. If we had a graph of any of these other things here, which we'll be doing, I think, in the very next lesson, but if you had a graph of these, you get this nice straight line. Every time you go, say, what was this last problem? That's right, kicks and feet down. Every time you go 4 more kicks, you go up 20 feet. Every time, 4 more kicks, up another 20 feet. It's always going to be the same. If the relationship was not constant, the diver is kind of going like this and like this, well then we wouldn't be able to tell exactly how far they've gone after so many kicks. So that's why it's important. It's important because it makes the relationship proportional, because it's a linear function, which it is a line. When we cross multiplied, we get a nice simple linear equation like we solved way back in 4.1. And this actually does graph to make a line. So that's why. So let's check out some other applications. Here it says, a baker can bake 10 loaves of bread in 3 hours. How many loaves of bread can be baked in 10 hours? Okay. One thing that I like to make sure I tell my students is make sure you have your labels in your proportion. Some people go through and they just start going, oh, there's a 10 and there's a 3 and there's a 10 and there's a something out. And I can't tell if what they did is right. I mean, there's 2 10s the problem. I don't know if this is this 10 or that 10, and it makes it very confusing for me to look at. And when the students mess up, they don't know why they made a mistake. So if you use labels, for example, the baker can make 10 loaves of bread in 3 hours. That's my label. Bread, hours. When you continue your proportion, the labels have to be the same going across. I should say they don't have to be, but I highly recommend they're the same as you go across. So bread, bread, hours, hours. Now, I can guarantee you're going to set this up correctly, because if you read the rest of the problem, it says, how many loaves of bread can be baked in 10 hours? And I know that 10 hours is going to go down here because that's the number of hours. This is the thing we don't know. How many loaves of bread? How many? It's a variable. So now when we cross multiply, we're going to get our answer. 10 times 10 is 100. 3 times x is 3x. Our little linear equation, we solve it, divide by 3 on both sides, and x equals 33.3. And x was the amount of bread. So in 10 hours, he could bake 33.3 loaves of bread if he's working at a constant pace. All right, letter B. It says, on TV, it takes 30 minutes to show 21 minutes of a show because of commercials. And that's actually true. If you watch a TV show like, say, SpongeBob, and you watch 30 minutes of the show runs for 30 minutes, you're only actually watching 21 minutes of SpongeBob. The rest of the time are commercials. Okay, so that's kind of what it's saying. And then it continues to go, if a movie's run time is 140 minutes, how much longer would it take to watch the movie on TV with commercials than on a TV with no commercials? Okay, so we're looking for the difference of commercials versus no commercials. Okay, this is our final goal. This is the answer to the problem, what we're trying to find. So let's see if we have everything. Do we know how long it would take to run the show with commercials? No. Do we know how long it would take to run the show with no commercials? Yeah, a movie's runtime is 140 minutes. That's how long the movie is. So if there's no commercials, there's no interruptions, there's no breaks, it's going to take you 140 minutes to watch that movie. So what we have to figure out is, how long would it take to watch the movie with commercials? So this is our missing piece. Time with commercials. All right, so that's what I'm trying to find out right now. How long will it take us to watch the movie with commercials? Well, since the amount of time the show's running and the amount of commercials, it's always constant. It's always 9 minutes for a half-hour show. That's 9 minutes of commercials for a half hour it's running on TV. So if you watched a show that's an hour long, like a cop drama or something, it's going to be 18 minutes of commercials and 42 minutes of show. That's how it always works out. So I can use that relationship, since it's a constant relationship, I can use that relationship to find out how long this would be using a proportion. So let's see. My relationship is for a run time of 30 minutes. So the show runs on TV for 30 minutes. You get 21 minutes of the actual show. The rest of the time would be the commercials. And I'm trying to find out the time with commercials, which would be the runtime. So I don't know this, but I know the show, the movie, is 140 minutes. And in this particular example, do you notice how I put these extra things out here, the runtime of the show? Ooh, that was interesting. That is important because my labels in my proportion are all minutes. And so it'd be confusing with the minutes. So this extra little piece out here just shows me this is how long it's on TV, and this is how long the actual show is. And since we have a proportion, we're going to cross multiply this thing. That side and that side. This side I can do in my head. That's 21x. The other side I can't. 140 times by 30. $4,200. And divide by 21. X equals, divide by 21 equals 200 minutes. So that's how long the show would run with commercials. A 140-minute show would take 200 minutes. So with commercials is 200. Without commercials is 140. So now I can do this problem. It asks, how much longer would it take? What is the difference in the time between with commercials and without commercials? So my little subtraction here tells me the answer is 60 minutes longer to watch the show with commercials than without the commercials. So if you watch a normal length movie on TV, it's going to take you about approximately 200 minutes, almost 3 hours maybe, 2 hours maybe. A little bit less than 2 hours. But if you'd watch it, or a little bit longer than 2 hours, if you'd watch it without commercials, it's going to take you an hour shorter, 60 minutes less with no commercials than with commercials. Here's one for you to try on your own. This is letter C. It says a car can travel 350 miles on 11 gallons of gas. How far could it travel with 50 gallons of gas? Go ahead, pause the video, try it on your own right now. When you're ready to continue, hit play, and we'll go through it together. So let's see here. So my things I'm measuring are the number of miles, the number of gallons. So if I go 350 miles on 11 gallons of gas, how far could you travel? I don't know. With 50 gallons of gas. Because the relationship is constant, I can use a proportion. And we cross multiply. That gives me 11x. The other side, I don't know. 350 times by 50. 17,500. Divide by 11 on both sides to solve the equation here. Ooh, extra little line in there. Cancels out. X equals, divide by 11 equals 1590 point. Looks like it's repeating decimal. 1590.90 repeating. So approximately 1590 miles it could travel in that amount of time. Letter D. Chase gets a weekly allowance of $3 for doing his chores. His brother Bruce also gets a weekly allowance of $3 for doing his chores. If the brothers put their money together, how long would it take for them to buy 4 games they want at $59.99 each? Go ahead, pause the video, try the problem on your own. When you're ready to continue, hit play, and we'll go through it together. Okay, so what's being measured here? Definitely we've got money, the amount of money they get. And the thing it's asking about is how long would it take for them to buy these games? Well, the amount of length it's telling us, the weekly allowance, they get amount of money per weeks. So let's use that. They each get $3 a week, Bruce and Chase together. So if they put their money together, they would get a total of $6 in 1 week. Okay. And we want to know how long, we don't know how many weeks, that's our variable, how long will it take for them to buy 4 games at $59.99? So I'm not going to put $59.99 here because I want to buy, or they want to buy, 4 games with that much money. So how long would it take them? So 4 times by $59.99. Let's see. Clear. 4 times $59.99 is 239.96. 239.96. So here's our new proportion. They get $6 each week. How many weeks will it take to make $239.96? That's what we're going to figure out. So they gave us some extra information here. We just had to figure out what it means and how to plug it in, but it didn't really complicate the problem that much. So let's cross multiply. We've got 6 times x is 6x. 1 times 239.96 is still 239.96. Divide both sides by 6, and we get an x value of, divided by 6 equals 39.99 weeks. 39.99 weeks. What do you think about it? I mean, your parents don't pay you a little bit early each week, so they're going to have to wait the full 40 weeks before they have enough money. At 39 weeks, they don't have enough. At 40 weeks, they do. So they're going to have to wait 40 weeks, or, I mean, they could buy a game here and there, but it's going to take them 40 weeks to afford all 4 games they want at the almost $60 a piece. There we go. Letter E. Factory A makes brooms at $3,405 per week. So every week they make that many. Factory B makes brooms at $499 per day. In 4 weeks, which is 28 days, which factory will have made more brooms, and how much more? Go ahead, pause the video, try it on your own. When you're ready to continue, hit play. We'll go through it together. Okay, so we're talking about 2 different factories here. We've got Factory A and Factory B. Excuse me. And we want to know, in 4 weeks, who has made more? And how much more? So these are what I'm trying to figure out. Who made more and how much more? So let's figure out how many each of these guys made in 4 weeks. So Factory A makes brooms 3,405 in, what's that? In per week. So in 1 week. And we want to know how many they're making in 4 weeks. In 4 weeks, x. Cross multiply this baby out. We've got 1x here, which is just x. Don't need the 1. And 4 times that big ugly number. Clear, clear. 4 times 3,405 equals 13,620. So Factory A made this many brooms in 4 weeks. Okay, Factory B. They make 499 per day. So brooms 499 in 1 day. So in the 4 weeks, which it tells us is 28 days, how many brooms would they make? And so we cross multiply. That still gives me 1x, which is just x. 28 times by 499. My calculator's always in the wrong space. 48. Oh, not 48. 28 times by 499 equals 13,972 brooms in that same amount of time. So, which factory made more brooms in that amount of time? Who made more? Well, Factory B. So Factory B made more brooms because that number is bigger than that number. That one's pretty easy. Now, how much more? How much more is a subtraction? You're trying to find the difference, the amount of space between here and here. So to find out how much more, we're going to take the 13,972 minus the 13,620 minus 13,620 equals 352 more brooms. We'll say factory B made 352 more brooms than factory A in 4 weeks. And there we go. So factory B made more brooms by that much. We figured it out by using our proportions. Each proportion was slightly different because this guy was based off the number of weeks. Factory B was off the number of days, but we could still cross multiply and solve both of them. If you could please, how are proportional relationships useful when solving real-world problems? Go ahead and pause the video right now, answer your question, and when you're ready to continue, hit play. We'll go through it together. This answer is kind of like a wraparound answer, but it says proportional relationships are useful when solving real-world problems because the relationship is constant. Therefore, a proportion can be used to solve the problem. That's basically what it comes down. Because it's a proportional relationship, you can use a proportion. Proportions are easy to solve, so therefore the problem's easy to solve, yada, yada, yada. This has been lesson 4.5. Thank you for watching.